Welcome back to abstract algebra and our discussion about permutations. Last time we were together in our last video, we were talking about even and odd permutations, and we promised to prove a couple of results that we stated simply as facts in our last video. So we're going to start over here with title page, even and odd permutations, and do a quick review of what we did last time, right? We showed last time, or at least we said last time, that every permutation can be written as a product. And I should point out, every time we say product here, we're talking about composition. That's the operation under consideration whenever we're talking about permutations. The default operation is composition, unless we say otherwise. So we've shown actually that every permutation can be written as a product of transpositions, and we had a little pattern by which we were able to do that. We'll review that here in just a moment. We also claimed that if a permutation is the product of an even number of transpositions, then it cannot be written as the product of an odd number of transpositions, and vice versa, right? Part one up here says that we can always write a permutation as a product of transpositions. Of course, it's either going to be an even number or an odd number. If it is an even number of transpositions that we're able to use, then there's no way that we could refashion the permutation so that we could write it as an odd number of transpositions as well. Similarly, if it can be written with an odd number of transpositions, then there's no way that we can find an even number of transpositions whose composition is going to equal that particular permutation. So the goal of today's video, the goal for this lesson, is to prove this result. This result is not at all obvious. No reason on the surface to see that we couldn't write a permutation with perhaps 5 transpositions, and then again as the product of, I don't know, 12 transpositions. But it is the fact that we can only write it with an even number or as an odd number, and we want to prove that today. The outline for this proof is as follows. We're going to start by looking at the identity permutation, and what we're going to show is that no matter how we write it as a product of n transpositions, that n has to be an even number. Right? In other words, we're going to show that the identity permutation can be written as an even number of transpositions, but not as an odd number of transpositions. Actually, the fact that it can be written as an even number of transpositions is trivial. For example, if I took say the transposition 2, 3, and I multiplied 2, 3 by itself, well, whenever every transposition is its own inverse, right? This transposition sends 2 to 3, but then this picks 3 back up and sends it to 2. So the composition of these two sends 2 to 2. It sends 3 first to 2, and then 2 goes to 3. It sends 3 to 3. And all the elements that aren't identified here are fixed by the transposition 2, 3. So this transposition sends 5 to 5. This picks 5 up and sends it to 5. Right, so this is the identity permutation, and I was able to use 2 transpositions to express it. I could have also used 4 transpositions to express it, and so on, right? But what we're going to prove is that if I can express it with n transpositions, then n has to be even. All we've shown so far is that it can be even. We're going to show it must be. Once we've shown this, once we've shown that the identity permutation can only be written as a product of an even number of transpositions, we're going to use that fact to show that every permutation is either going to be written as an even number or as an odd number, but never both. Right? We're going to show that if a permutation can be expressed as the product of an even number of transpositions and also as the product of an odd number of transpositions, right, we're going to show that if there were such an animal, then the identity permutation could be expressed with an odd number of transpositions. Well, at this point, we will have already shown that to be impossible. And so the only place we could have erred in our reasoning here is in our supposition that we did have a permutation that could be so expressed. One way is the product of an even number of transpositions, and another way as the product of an odd number of transpositions. And so that contradiction that we're going to establish is going to prove that a permutation can only be expressed with either an even number or an odd number of transpositions, but never both. Okay, but before we get started, before we begin this proof, I want to make a few observations. All right, first of all, I want to observe that the 3 cycle, we're going to use 2, 5, 4. It's not really important what that 3 cycle is that we're working with, but we're going to show that we're going to observe that 2, 5, 4 can be written as the product of 2 transpositions, T1, T2. I'm abbreviating the transpositions here with just symbols. So T1 is some transposition, T2 is some transposition. I'm going to do this in such a way that 2, right? 2 is the first element in this cycle. That 2 belongs to T1, but doesn't belong to T2. Right? Now I'm going to fail if I use the technique that I had used before to write cycles as products of permutations. Right? What we had done is written down the 2, right? The first number, and then the last, and then the first number and the next to last until we were done. Of course, with the 3 cycle, we are done at that point. So 2, 4, 2, 5 is, and you can verify this very quickly by compose these 2 transpositions together. I do get 2, 5, 4. Now, this doesn't do the job because while 2 does belong to T1 here, this is T1. Right, this is T2. 2 belongs to T1, but it also belongs to T2. So that doesn't do the job I'm looking for. But I could rewrite 2, 5, 4 as 4, 2, 5. Right? It's the same permutation. This sends 2 to 5. This sends 2 to 5. This sends 4 to 2. This sends 4 to 2. This sends 2 to 5. This sends 2 to 5. Or I guess we did that one, 5 to 4, 5 to 4. They're the same function. They're the same permutation. And if I use my algorithm to write this cycle as a product of transpositions, I'm going to have 4, 5, 4, 2. Here we go, right? 4, 5, 4, 2. Now that also doesn't do the job, right? 2 does not belong to T1 in this case. But try one more time. I can also write this cycle as 5, 4, 2, right? 5's going to 4, 4's going to 2, 2's going to 5. Just like it did up here. 5's going to 4, 4's going to 2, 2's going to 5. But whenever I use my little algorithm on this one, I get 5, 2, 5, 4, and sure enough, 2 does belong to T1, but it doesn't belong to T2. Right? So I can always figure out a way to express my 3 cycle as a product of transpositions so that this first number belongs to T1, but not to T2. Of course, I could also generalize this by rewriting it some other way. If I had written it this way, I could have argued that I could write it so that 4 belongs to T1 and not to T2. In fact, one of these probably shows that. In fact, this one does, right? Here, 4 belongs to T1 and not to T2. Here, 5 belongs to T1 and not to T2. So I could do this with any of those 3 numbers. I'm just focusing on 2 now for illustration. So I think that from this example, we could argue more generally that every 3-cycle ABC can be expressed as the product of 2 transpositions, T1 composed of T2, such that A belongs to T1 and A does not belong to T2. I'd like you to include that as a homework exercise. It's one of the ones in the notes. I don't remember which one at this point. So let's do an example. So I want to show that this permutation right here, right, it's a product of 5 transpositions, but altogether it's a permutation. It's one permutation. I want to show that we can write this as a different product of transpositions, such that 2, right, 2 belongs to this transposition right here. I want to show that I can write it so that 2 belongs to the first transposition, but not to any of the other ones. Right, and here's how I'm going to do that. So I'm going to begin by rewriting this permutation. All right, I'm going to write the first 3 down. I'm going to focus on these last 2 to start. You showed in a homework exercise that either 2 transpositions, if they're disjoint, well, if they're disjoint, I could just interchange them and I'd have exactly the same transposition again. These aren't disjoint, but your homework exercise showed that if they're not disjoint, then either the product is the identity, in which case these would both be the same transposition, or the product is equal to a 3-cycle. Well, that's what we're going to have here, right? They're not the same and they're not disjoint. So I know I can write this as a 3-cycle. What is that 3-cycle? Well, let's see. 2 is going to get sent to 4. And then this fixes 4. So 2 is going to get sent to 4. 4 is going to get sent to 2. But then this picks up 2 and sends it to 5. So 4 gets sent to 5. And 5 better get sent to 2. Let's double check. So this transposition fixes 5. But then this sends 5 to 2. So sure enough, we have a 3-cycle there. And now I want to rewrite this using the idea that we had up here, that every for a 3-cycle, I can rewrite it so that whichever number I choose appears in the first transposition, but not in the second. So let's see if we can do that. In fact, let's go back up to this example up here to get a hint as to how that might work. Let's see. So whenever we finally were able to make it work, what we got was the, let's see, the middle term followed by the first, and then the middle term followed by the last, right? Middle term followed by the first, middle term followed by the last. All right, so 5, 2, 5, 4. So let's do that down here. Middle term followed by the first, middle term followed by the last. Let's double check that that works. It's just really 2, 4, 5. So let's see, this sends, that sends 2 to itself. That sends 2 to 4. That's what we want. 4 goes to 5 and then stays fixed. That's what we want. 5 goes to 4 and then to 2. So 5 goes to 2. Yep, that's what we want. Okay, so what we have now is we've rewritten this as a product of a new collection of transpositions so that the 2 is no longer in this last spot, right? There is no 2 in this last transposition, but it's it's bubbled down to the transposition prior to it. I want to try that again. This time I want to focus on these two transpositions. So I'll write the 1, 5, write the 3, 4, and then I'll do that same process, right? These are not disjoint. They are not identical. So I know I can write them as a 3 cycle. Which one? Well, let's see. 2, this sends 2 to 4, and this fixes 4, so 2 gets sent to 4. 4 gets sent to 2, and then this picks up 2 and sends it to 3. This sends 3 to itself, and then this sends 3 to 2. And then I'll have the 4, 5 from before. And now let's rewrite that 3 cycle so that 2 is in the first transposition and not in the second. So how do we do that before? It was middle first, middle last. So middle first, middle last. Go ahead and double check quickly for me that these two together does in fact equal 2, 4, 3. Okay, and so now we have 2 in this transposition, but not in either one of those. Do it again with these two. So let's see, 1, 5, and then let's see, this is going to send 2 to 4, but then this sends 4 to 3, so 2 goes to 3. 3 is fixed and then goes to 4, and then 4 goes to 2 and stays there. And then re-express this 3 cycle so that 2 is in the first transposition and not the second. So middle first, middle last. Right, and then finally do this one more time. Now we're going to do it with these two. Again, if they were disjoint, I could just interchange them and I'd have 2 here but not there. Actually, they are disjoint, aren't they? So I can do that, right? Since they're disjoint, right? This sends 2 to 3, but then this fixes 3. This sends 3 to 2, but this fixes 2, right? So whatever this does, this doesn't affect. So I can just interchange those guys. 3, 2, 1, 5, 3, 4. I'm going to write 4, 3 as 3, 4, right? Same, it's the same permutation, right? This sends 3 to 4, it sends 4 to 3. This one sends 3 to 4, it sends 4 to 3. Same thing. And so I've done exactly what I set out to do. I have 2 as an element of this transposition, but not as an element of any of the other ones. Now, that's actually very interesting, because the fact that I can write this permutation in this way, with 2 being, with this transposition being the only one in which 2 appears, this tells me for sure that the permutation I started with could not possibly have been the identity permutation. Think about that for a moment. Can you give me a quick argument as to why that would be the case? Well, let's think about this for just a moment. In fact, I could have, let's go back here, just one more. I could have rewritten this just another step further. Since 3, 4 and 3, 4 are next to one another, these two transpositions, this could be rewritten with these 2 guys eliminated, because these 2 together form the identity permutation. This sends 3 to 4, and then this sends 4 back to 3, so 3 goes to 3. Similarly, 4 goes to 4. Everything else remains fixed by that transposition. So actually, I could have reduced this by 2 more transpositions. So I could have written this as 3, 2, 1, 5, 4, 5. Right, and because I can do that, because I can write my original permutation with 2 in this spot and nowhere else, this can't be the identity permutation. Why? Well, this permutation sends 2 to 3. Right? It's the only place 2 appears, and so what happens up here, 2 is always getting fixed in all of these guys. Down here, 2 goes to 3. Well, the identity permutation doesn't send 2 to 3. The identity permutation sends 2 to itself. It sends 3 to itself. But this is going to interchange 2 and 3. Well, since this is just another way to rewrite this, this is going to interchange 2 and 3 as well. And so what I started with was not the identity permutation. I want you to try this. First of all, I want you to confirm, here's another composition of transpositions right here, right? 1, 5, 1, 2, 1, 4, 2, 5, 1, 2, 2, 4. I want you to confirm that this, in fact, is the identity permutation. I'll start here. Let's see. Where does this send? Let's say, where does this send the number 4? Well, this sends 4 to 2. This picks up 2, sends it to 1. This fixes 1. This sends 1 to 4. And these 2 fix 4. So all in all, 4 gets sent to 4. Well, that's exactly what we would expect with the identity permutation. The identity permutation sends everything to itself. So take a moment, confirm that, that this product of transpositions really is the identity. Hit pause. Okay, so did you check it out? Does it work? Yeah, it does. All right, so now what I want you to try to do is to use the procedure above to try to write this as the product of transpositions, T1, T2 through Tn, such that 2 belongs to the first transposition, but 2 doesn't belong to any of the other ones, right? Just like we did before. Just like we did right before, we rewrote our permutation so that 2 appeared in the first transposition, but not in any of the other ones. Give it a try. Let's see if we can do that. Hit pause, and then come back after you've made that attempt. Okay, what happened? Well, I'll tell you what happened. You weren't able to do it. You weren't able to do it because by the time you got to some position in here, the transposition that had the 2 in it, as it bubbled down, the transposition that had the 2 in it was next to itself. And so, well, let's just do it. So we've got, let's see, 1, 5, 1, 2, 1, 4, 2, 5, and then let's see, 1 gets sent to 2, 2 gets sent to 4, 4 gets sent to 1, right? This is the same as 1, 5, 1, 2, 1, 4, 2, 5. And let's see, it's 2 that I'm concentrating on. So let's see if 2 is in this first position. Let's move the 1 over here. So let's see, 4, 2, 4, 1, I think is gonna be the product of transpositions that I want, right? That bubbles the 2 down into this transposition and not that one. Try again. Let's see, 1, 5, 1, 2, 1, 4. Now concentrate on these 2. What 3 cycle is this? let's see, 2 is getting sent to 4 and then fixed. 4 gets sent to 2 and then to 5. 5 gets sent to 2. I'm writing 4, 1 is 1, 4, standard form. I just like it better, it's prettier. And then unpack that into 2 more transpositions. Let's see, 2 is the one I'm trying to bubble down, so middle first, middle last. 4, 2, 4, 5, 1, 4. Okay, so now let's see, I've bubbled it down from, let's see, 2 was in this last position, then it was in this second to last, now it's in the third to last position. One more time, 1, 5, 1, 2. It's now I'm going to work with these two, and let's see, this is going to send 2 to 4, then 4 goes to 1. It's going to send 1. This sends 1 to itself. This sends 1 to 4, and 4 is going to 2 and staying there. And the others, and unpack that again. So this is going to be what, 1, 2, 1, 4, 4, 5, 1, 4. Okay, so now we have 2 in the fourth to last position, and then none of the ones that follow. Oh, but look what happened. 1, 2 is right beside 1, 2. Ha! Well, these two together, that's the identity permutation. Right? 1 goes to 2, but then 2 goes back to 1 again, right? Every transposition is its own inverse. So I now have this as 1, 5, 1, 4, 4, 5, 1, 4. And in fact, 2 doesn't appear at all anymore. So there's no way I'm going to be able to get 2 using this procedure bubbled down to the bottom. This is exactly what I expected to happen. Since this is the identity permutation, it has to send 2 to itself. But if it sent 2 to itself, there's no way I could have 2 in that first position, because that would keep 2 from being sent to itself. Right? And notice also that whenever that transposition was paired up with itself, I was able to eliminate it along with the other copy, so that I was able to reduce the number of transpositions that I was using by a total of 2 transpositions, right? I was able to take, I originally was using 6 transpositions, now I'm using 4. If I tried to do this process again, let me do it over here. So let's see, I'm going to write 1, 5, 1, 4, and let's see if we can bubble this 4 down here so that 4 is going to be in the second to last transposition and not the first. Let's see, same idea. I'm going to send 1 that goes to 4, but then to 5. So 1's going to 5. 5 is going to 4. And then 4 goes to 1. Right, so I've got 1, 5, 1, 4. And let's see, I want to write this, right, I'm working with 4 now, I want to bubble 4 down. So let's see, this would be the same as having written, let's see, this is 4, 1, 5. I'm going to use that same algorithm I was using before. So 1, 4, middle first, middle last. Whoops, middle first, middle last, that's a 1. Okay, and oh my goodness, look at that. The 4 bubbled down to second to last, but it put it right beside a copy of itself. So I get to annihilate these 2 all at the same time. So now I can, right, so I've gone from 6 permutations, or I'm sorry, 6 transpositions to 4 transpositions to 2 transpositions, ha, to no transpositions at all. Now that's just the way I write no transpositions rather than having empty space, right? But this means no transpositions. This is the identity. This sends everything to itself. So no matter how I try to, whatever element I tried to bubble down to get down to the beginning, I'm always going to wind up with the transposition containing the number in question, right? In this case, the number in question was 2. Bubbled it down until 2 was next to, or 2 was in a transposition that was next to that same transposition. So I was able to annihilate those 2 at a time. Then I focused on the 4. I tried to bubble the 4 down, but whenever I did that, the transposition that the 4 was in eventually was next to itself. So I was able to annihilate those 2 at a time, until finally I was able to annihilate everything, and I did so 2 at a time. So that's what's going to happen whenever I have a permutation that is equal to the identity. What all of this shows is the following. If one can be written, if the identity permutation can be written as the product of n transpositions, then it can every time be written as the product of 2 fewer transpositions. If it can be written as the product of n transpositions, it can be written as the product of n minus 2 transpositions, right? We started here with 6 transpositions, whittled it down to 4, right? That's 2 less than 6. And then down to 2, that was 2 less than 4. And then down to 0, that's 2 less than 2. Well, if the identity permutation can always be whittled down to 2 fewer transpositions than it was before, then it turns out that we could not possibly have written it as the product of an odd number of transpositions. Why? Right? Well, if 1 could be written as the product of, let's say, 9 transpositions, well, then those 9 transpositions could be whittled down to 7, right? But then those 7 could be whittled down to 5, and then down to 3, and then down to 2 less than 3, which is 1. But a single transposition, like 2, 3, for example, is clearly not the identity, right? It's not the identity element, right? So if I started with an odd number of transpositions and kept whittling it down by 2, I'm going to get down to a single transposition. So those 9 transpositions could not possibly have represented the identity element. So in general, what this shows is that if the identity element is the product of n transpositions, then n has to be an even number. The identity permutation can only be expressed as the product of an even number of transpositions. The full result now follows pretty easily. Because if I take any permutation, let's call it F, any permutation at all, let's say there is one out there that could be written as the product of, well, an even number of transpositions, right? T1, T2, up through T sub 2n. I'm using this to indicate an even number. So F is written as an even number of transpositions. And let's say it can also be written as the product of an odd number of transpositions, right? So I'm using 1, 2, and then 2m plus 1. That's an odd number. So I'm indicating that, this is an odd number of transpositions here. So all my T's and my S's are transpositions. Well, if I can do that, notice that, well, I don't know if we've pointed this out before or not, but it's pretty straightforward. If I have a bunch of transpositions, right, and I write them in reverse, so 2, 3, 4, 5, 2, 4. If I write them in reverse, 2, 4, 4, 5, 2, 3. If I write them in reverse, look what happens whenever I compose all that together, right? That's going to be the identity element. Then these two guys are going to be sitting next to each other. So that's going to be the identity element. And these two guys are going to be sitting next to each other. So that's the identity element. So in other words, if I write, I'm going to, let's write these in reverse order. If I write these in reverse order, what I have is the inverse of F, right? If I write them in reverse order, I get the identity. And so F inverse is, well, this product transpositions written in reverse order. And so since the identity is going to be F composed with its inverse, what I have is that, let's see, F is written this way. So there's F. So there's F. And here's F inverse, right? So I have F composed with F inverse being the product of all of these guys. But what is this? Well, it's an odd plus an even number of transpositions. It's an odd number of transpositions. I've just written the identity permutation as the product of an odd number of transpositions. But I know that's impossible. We just showed that that the identity can only be written as the product of an even number of transpositions. So the only flaw in our logic here is assuming that there is such an animal F, a permutation F, that can be written as both an even and an odd number of transpositions. That leads to a contradiction. And so that gives us the result that we were looking for. This shows that, and I have this listed as theorem 154 in the notes, very, very important theorem, that a permutation can either be expressed as the product of an even number of transpositions or as the product of an odd number of transpositions, but never, never both. For homework, I would like you to do two things. First of all, consider the permutation that's expressed as the product of these 5 transpositions, and show that this is equal to the cycle 2, 5, 4, 3. All right. After you've done that, what I want you to do is use this bubbling down procedure that we were talking about in this lesson to show that that this product, if I start with this product, I can start with it so that and then rewrite it so that whenever I'm done, I have the product of a new set of transpositions in such a manner that 4 belongs to this one right now. I want you to bubble it down so that 4 belongs to T1, but not to any of the other transpositions, right? We kind of expect that we should be able to do that since the entire permutation sends 4 to 3, right? So we expect that to be able to work, but go ahead and verify that by using the procedure that we talked about, right? And then also show that I can't do this with the number 1, right? And we don't expect to be able to, right? This permutation fixes 1. And so if we could bubble the transpositions down, the ones that had 1 in it, if we could bubble it down so that 1 was in the first transposition and not in any of the other ones, well, that would be contradicting my observation that 1 gets fixed by this permutation. Right. So by doing this, I think you're going to help to solidify some of the ideas that we've talked about in this lesson. Do that, and I also want you to prove theorem 148. That was the one we talked about earlier. Couldn't remember the theorem number at the time, but it's theorem number 148. And if you'll do those two, I'll do them as well, and we can compare answers in another in another lesson. So thank you very much for joining me for this discussion on even and odd permutations. It was a very important set of results, and ones that we're going to be using many, many times to prove other theorems in the future. Until then, stay safe, stay healthy. I'll see you next time.